Welcome back. Let's learn some momentum. All right, so we're jumping into chapter 9 of college physics, the AP edition, this beautiful baby. So chapter 9, let's start by introducing the idea of impulse. So impulse is represented by letter J. Because we've already used J for joules as a unit, and impulse has no J's in it. So yeah, yep, J is impulse. And impulse is equal to the average force times the change of time. So the amount of time that that force is exerted for. So this is during a collision. So for example, if I took this ball and I whacked it for 1/10 of a second, like this, boop. That was probably less than 1/10 of a second, maybe 1/20th or 1/100th of a second. Oh, look, the ball came back. Then I would be exerting a force on it for a certain change of time, and that's during that collision. Now, we can find the impulse because it's the area under a force curve. The unit for impulse would be newtons times seconds. That's force unit times the time unit. Or that's equivalent to kilograms meters per second. And we'll see why that matters in a little bit. So just in terms of showing what that means, if I'm looking at the area under the force curve, this is force versus time. So force is on my y-axis, time is on my x-axis there. And it would be the entire area under the curve here. All right, so all of that is the impulse. Or because I'm taking a force average, I could take like some sections here that would normally be above it and push it down to here and take this section and push it over to here. And then I make a nice rectangle. And then that makes it easier to calculate because it's the average force times the total amount of time. And the total amount of time starts there and there. So same time duration, but now I've made it an average force. No worries. All right. So let's stop and think about impulse. We have two graphs, graph A and graph B. Graph A is the force versus time graph for a hockey stick hitting a 160-gram puck. Graph B is force versus time graph for golf club hitting a 46-gram golf ball. Which force delivers the greater impulse? Okay, so remember, impulse is force times time, or average force times time. So in this case, it's 300 times 5 milliseconds. That'd be 1/1000th of seconds. So that'd be 0.005 seconds. Force B is 150 times 10 milliseconds. Well, 10 is twice 5, and 150 is half of 300. So if I multiply these, I would get the same answer of 1,500 Newton milliseconds, or 1.5 Newton seconds. In each case, 1.5 Newton seconds is the area in there. So those appear to be the same. Both forces deliver the same impulse. Cool. All right. Now, let's take a look at momentum. So momentum we represent with letter P because we've already used J, so we may as well use lowercase p for momentum because of all the P's in it. I don't know, man. I don't know. So P is equal to the mass times the velocity. Momentum equals mass times velocity. And we can break that down into X and Y components. Now, mass doesn't have an X and a Y component. Mass is mass. It's the amount of stuff that's there. But velocity does have an X component and a Y component. So I could find the X component of momentum, the Y component of momentum, and then I could put them together in a triangle, a right triangle, to find the total momentum. A squared, B squared, C squared, or use our trigonometric functions with an angle. Either way could work. Now, the reason that we're talking about momentum and impulse is that they are equal to each other. Impulse is equal to the change of momentum. Now, if I solve those both out, I could say impulse, which is force times the change of time, is equal to momentum, which is equal to the mass times the change of velocity. Ft equals mv. All right, now just as a point of reference, some typical momenta for various things. A falling raindrop has a very small mass, momentum of 10 to the negative fourth, 1/10,000th kilogram meter per second. A bullet has a lot of speed, but not very much mass, so not very much momentum. A pitched baseball has less speed, but a little bit more mass, so a little bit bigger momentum. A running person has much bigger mass, even though it's going slower. So that's 200 kilograms meters per second. And then a car on a highway has a lot of mass, going pretty fast, so lots and lots of momentum, right? The mass matters and the speed matters. Even though the bullet is the fastest thing, it's a really, really small mass thing, so not very much momentum. So why do bullets do damage? Well, because they're going so fast and they have a lot of pressure, so they go into things. And that's where the damage occurs. Not necessarily the momentum, but the fact that it's going in and breaking things, like organs. Okay, so another thing, since impulse is equal to the change of momentum, if I break the change of momentum here into momentum final minus momentum initial, I could say that the final momentum is equal to the initial momentum plus the impulse that you exert on it. So I've got something that's moving, and then I put an impulse on it, and then I make it move faster or opposite direction or slower. I can add the original momentum plus the impulse to get the final momentum. All right, let's stop and think again. A puck seen from above was moving with an initial momentum when it received an impulse from a hockey stick, giving it the final momentum shown. Which arrow best represents the puck's initial momentum? Okay, so the impulse is going to go to the right. Now I know that the impulse plus the initial momentum will equal the final momentum, so I have to end up going that way. I've already got that component, right? I've got the sideways to the right component. The final momentum is upwards to the right, so I'm going to guess that I need some up to it. So I'm going to need something to be going up like that way, so that I end up with something over there. Let's see. And the one that has an upward component is D. D is the only one with an upward component. E is going down, B is going down, A and C are going horizontally. So it has to be D because it has an upward component. And my final momentum also has an upward component. Okay. Let's do some practice problems. So calculating the change in momentum. A ball of mass of 0.25 kilograms rolling to the right at 1.3 meters per second strikes a wall and rebounds to the left at 1.1 meters per second. What's the change in the ball's momentum? What's the impulse delivered by the wall? Okay, so I'm looking for the change in momentum. And first I just want to note that ball was rolling to the right at 1.3, so that's a positive 1.3 at the beginning. And then it rebounds to the left at 1.1, so that's a negative 1.1, right? Going back the other way to the left is negative. All right, so I know impulse momentum is what I want to solve, and conveniently, the impulse is equal to the change in momentum, which is equal to the mass times the change of velocity, and which is equal to the mass times velocity final minus velocity initial. Okay, so the mass of the ball is 0.25 kilograms. The velocity final is negative 1.1 meters per second minus 1.3 meters per second. Negative 1.1 minus 1.3 is negative 2.4. So I'm doing negative 2.4 times a quarter. which should give me negative 0.6. Yeah. So my change of momentum is negative 0.6 kilograms meters per second. Make that the whole thing. And then the other part is what is the impulse delivered by the wall. And the impulse has to be the same. So the impulse is also negative 0.6 kilograms meters per second. Looking good. Okay. Other things that we know. So I could also say that the average force is the negative initial momentum over time, over the change of time. That's P equals M, or sorry, momentum equals impulse, solve for force. So force is momentum over time. And then the initial momentum is negative M times the initial velocity divided by the time of impact. So what does that mean? What it means is if I want to make things safer, and this would be like in a crash, right? In something like a crash or a collision, where I'm going fast to not moving at all, right? Objects coming in and then stops. So if I want to be safe as this object, I need to increase my time of impact in order to decrease my force, because time of impact is down here in the denominator. If this value gets bigger, the force will get smaller, right? Larger time, smaller force. They are inversely proportional to each other. So I got to play around with trying to increase my time of impact. And that's what things like airbags do. That's why the front of cars have crumple zones. So they crumple, and that increases the time that you're impacting to reduce the force on the passengers inside. It ruins the car, but it keeps the people inside safe. It's also how helmets work. Increases the time that your head is hitting the ground instead of having your head bounce right off the ground. That'd be bad. All right, another stop and think. The cart's change of momentum. So before the cart was going this way, that is to the left, so that's a negative 2, right? Times 10 would be negative 20 initial. Final is the same cart, which is 10 kilograms, times 1, so that's 10 kilograms meters per second. Final minus initial is 10 minus negative 20, which gives me positive 30. So final minus initial, boom, there we go. All right, let's do a couple more examples. Force in hitting a baseball. A 150-gram baseball is thrown with a speed of 20 meters per second. It's hit straight back towards the pitcher at a speed of 40 meters per second. The impulsive force of the bat on the ball has the shape shown in figure 910 right there. What is the maximum force that the bat exerts on the ball? So the bat exerts a force up there, okay. What is the average force that the bat exerts on the ball? Okay, so I need to find the, obviously the average will be half of the maximum here, since it's a straight line triangular. But let's do average. I think I'm going to calculate the average first and then do the maximum, because the maximum is clearly twice the average. So I know that mv is my momentum, and that'd be the change of velocity, and that's equal to the force average times the amount of time. Okay. And I have the amount of time right here, 0.6 milliseconds, which is 0.0006 seconds. Okay, so I'm going to convert it into full seconds. Now, the mass of the ball is 150 grams. That's 0 0.150 kilograms times the change of velocity. So it came in at 20 and then hit straight back at 40. So one of these has to be negative. And then when I subtract them, the difference is going to be a difference of 60 meters per second equals the force times 0.0006 seconds. And this is going to be my average force. Okay. Solve for force average. And that will be 0.15 times 6 divided by 0.0006. 1,500 newtons is my average force. And since it's triangular shaped and straight lines, I know that my maximum force has to be twice as much. So that would be 3,000 newtons is my maximum force. Nice. Let's do another one. Height of a bouncing ball. Ooh, I bet this is going to have some kinematics in it too, going back to those motion equations. Cool. A 100-gram rubber ball is thrown straight down onto a hard floor so that it strikes the floor with a speed of 11 meters per second. Shows the force that the floor exerts on the ball. Estimate the height of the ball's bounce. Okay, so it appears to go 5 milliseconds of time touching the ground. That's equivalent to 0.005 seconds. The maximum force is 800 newtons, but to find the impulse, it's probably going to be like the halfway up, right? It's not perfectly linear, but it's got kind of a parabolic shape with the S curve, and I reckon that section is pretty much equivalent to that section. So I'm going to estimate it at about an average of 400 newtons, because it says estimate, right? It doesn't give us precise values, so I can do that. So 400 newtons times 0.005 seconds will give me J, right? Now I need the height though. It strikes the floor with a speed of 11 meters per second. So the momentum in will have to equal the momentum out, I am guessing. So if I run through that, that'll give me, All right, so let's start by finding my impulse. My impulse, since I've done the work for that, is going to be the force average times the change of time, which is equal to 400 newtons times 0.005 seconds. Let's do the math on that. Gives me 2.0 newtons times seconds, or kilogram meters per second, right? Same units either way. Now I need to figure out my post-collision velocity. So the impulse, J, is equal to the change of momentum, and the change of momentum is equal to the final momentum minus the initial momentum. Okay? Now, I know about the initial momentum, that one. And I know that it's going straight down at an initial momentum of mv, so pi. Oh, okay, good. I have a mass and I have a velocity. All right, this is working. Okay, I think I'm getting somewhere. So initial momentum, I'll do this in a different color so we can keep it track. My initial momentum is equal to the mass times the velocity, which is equal to 0.1 kilograms times the initial velocity of 11 meters per second, right? That was my starting velocity. That gives me an initial momentum of 1.1 kilograms meters per second, but it's going down. So that has to be a negative 11, which makes that a negative 1.1. Now I can say that J equals P sub F minus P sub I. 2.0 kilograms meters per second equals P sub F which is what I'm solving for, minus negative 1.1 kilograms meters per second. So something plus 1.1, that gives me a final momentum of 0.9 kilograms meters per second. And I know that is equal to the mass of the ball times the final velocity. Whew. The mass is still 0.1 kilograms times the final velocity. So divide both sides by 0.1. My velocity final has to be 9.0 meters per second. All right. That, however, is not what I'm being asked for. Now I know that it's coming back up at 9 meters per second. So that's just an indication that when the ball bounced, it lost some energy due to deformation, like the ball squished, and so it wasn't a perfectly elastic collision. All right. Now I need the height. So I need the y, right, final y. I'm given a final velocity, but this is now my initial velocity, right? This is now how fast it's coming up. So that now becomes my initial velocity. I know at the end, I'm going to go up to the top and it's going to go to 0, right? Because it's go up, stop, and then back down. So I'm also given that v sub f equals 0 at the top of the height. I know that my acceleration is negative 9.8 meters per second squared. And I need a distance. So now I'm going to check my equation sheet, my physics everything equation sheet. And that gives me, okay, pretty sure that we can go back to v sub f squared equals v sub 0, or v sub I, y squared plus 2a change of y. V sub f is going to be 0 squared equals 9 squared plus 2, 9.8 meters per second squared, change of y, negative 9.8. So negative 81 as the 9 shifts over here, negative 81 divided by negative 19.6, 81 over 19.6 gives me 4.1 meters high. So my change of y is 4.1 meters, and that is how high the ball should bounce. And if I check, they gave it as a single digit 4, but looks like we're in the right space. Wonderful. All right, let's do a stop and think again. A 10-gram rubber ball and a 10-gram clay ball are each thrown at a wall with equal speeds. The rubber ball bounces, the clay ball sticks. Which ball receives the greater impulse from the wall? Oh, okay. So if the clay ball goes in and sticks, it came in at the same speed, and then it went to 0. So its change of velocity is 1 amount. The rubber ball bounces off. So because it bounces off, it went from positive to negative, which gives it a greater change of velocity. It had to have a greater change of velocity, so it has a greater change of momentum and thus a greater impulse. So the rubber ball, anything that bounces, has a greater impulse than anything that sticks. So the rubber ball, because it bounces. Nice. Okay. So that is going to conclude part 1. And then we are going to come back and do conservation of momentum in just a second.